Hello everyone. Today we'll talk about the solution to the problem most beautiful item for each query. When thinking about this problem, it quickly becomes apparent that there will be some sorting involved. The most obvious place for sorting is the fact that every query has some cutoff price, and we are interested in getting the biggest beauty from among all the items whose price is not greater than this cutoff price. And that means that if we sort our items in increasing order by price, then for a given query, we are given some cutoff price. So there will be some position in our array such that to the left are all the elements that cost at most this price for this query, and items to the right are too expensive. And the answer is the maximum over all of those values. So that means that the answer for every query is a prefix maximum over all the beauties in this array. We can calculate those prefix maxima and store them along with the prices. And then for every query, we can just binary search the value in this array. Now this requires us to write binary search. It's of course an q log n solution. And it also has the benefit of being an online solution, which means that we can answer a query before reading the next one. Because sometimes it's necessary for us to solve queries online. But since we're given all the queries immediately, we can afford to do some other things and solve the problem offline. And of course, as I mentioned about sorting, what if we sort the queries array? We'll still be maintaining the sorted items array, but now if we sort the queries array, then we can process queries from queries with the lowest cutoff price to queries with the highest cutoff price. And in that case, the cutoff price will just be increasing and increasing, which means that we can go a single time through our prefix maximum array, just pushing the cutoff price to the right, and answer all our queries. Now, the actual time complexity of both of those solutions is not the same, so I'd say that this is just a matter of preference which you implement. It's not like the offline solution is better when it comes to time complexity, and it has the downside of being offline. And I think it's a simpler solution to write, and it can also showcase, well, I guess both of those have a little bit of a tricky part, because for some people binary search would be tricky, and maybe for some people, when it comes to solving the problem like this, using that, actually sorting the queries in such a way that we can restore their original order when filling out the resulting list might be a bit tricky, and I'll showcase this second part in my solution here. So, since we'll be answering all the queries offline, we first allocate the list for answers for all the queries. We sort the items. This is the only thing. We don't care about sorting by beauty, we don't care about the order of beauties, we only care about the price being increasing or non-decreasing. And we'll be maintaining the pointer to the next item that we've not processed yet, and the biggest item we've seen previously, so we don't have to maintain an explicit prefix maximum array, we just have to maintain the current maximum. And now, to achieve this arg sort, to achieve this sorting of queries in such a way that we can restore their order, instead of just sorting queries, we'll sort numbers from 0 to len queries, not inclusive, so they're indices, but we'll be sorting them in such a way that their order is the same as the relative order of queries. So we just create a list of this range from 0 to len queries, we sort it, and we can use the Python's key function so that when Python, for instance, has to compare 3 with 7, it compares queries of 3 with queries of 7 and puts their order in exactly the same way as if it was ordering the queries array. And now what we have then is that we can go for I in order, so those will be the indices of queries. We get the query corresponding to our index, so this is the cutoff price. We push the right end forward, so the next item forward, for as long as we can afford it, so for as long as its price is less than or equal to the query's cutoff price. And at every point we remember if this is the new maximum. And of course we have to make sure that we don't fall out of the array. And at the end, the result for this current query is equal to the biggest, to this variable biggest. and we have to write it in the corresponding position in this list. So the list at position I is equal to biggest. And at the end we just return the result. So again, the only tricky part might be this arc sort. This is a very useful pattern, so it's nice to, have the ability of writing it. And as an example, maybe this order array might be something like 2, 1, 0, 4, 3. And that means that the second query has the smallest price, then the first query, then the 0th query, then the 4th query, and the third query has the highest price. And we will be calculating the results first for the second query, then for the first query, then for the 0th query, then for the 4th, then for the 3rd, and this will be our resulting array.